All right, so let's solve number of wonderful substrings. This is a medium problem, but I would say it's personally on the harder side because there's only one approach slash solution and it's a little bit unintuitive, but I'll sort of explain how it works. So in this question, I won't go in depth, but basically put a wonderful string is a string where at most one letter appears an odd number of times. In this example, these are all wonderful strings, but they do not include A, B because A and B occur an odd number of times. So this is two numbers, but they say it's at most one can be valid. And if you look here, again, the same thing, A, B is not valid. So in this question, it talks about odd and even. And rather than counting the frequency, like A appears 9 times, we're more interested in seeing, well, A appears an odd number of times. And because of this parity, this kind of leads you to think, well, let's solve this problem with bit manipulation, right? Because bits have two states, right? Let's say 0 is going to represent being even, and let's say 1 is representing being odd. Also, we know that all the letters in the string are between A and J. Specifically, these are 10 letters. So why not represent any string by these 10 bits? So I'm just going to write out 10 bits. And let's say, how can we represent maybe like ABA? Well, let's say this represents the parity of the occurrence of A, and this represents the parity of J. In this case, because let's say we loop through this, right? We see an A, that means we flip it to a 1. We see a B, we flip this to a 1. We see an A again, and then we flip it to a 0. What this tells us is that in this string, we have a single odd occurrence, and in this case, it's just a B. Is this a valid wonderful substring? Yes, it is, because there's just only one character that occurs an odd number of times. Let's say we had a D in here, like right here, then this would flip this toggle. And now you have two digits that are a 1 in this binary representation. And if you ever have more than one of these, then it's not a wonderful string. In this case, because you have 2, it's not a wonderful string. Okay, so it's very easy for us to tell if a string is valid or not by basically using this bit representation and checking, well, is there more than one 1? But now the question comes, we want to find all these substrings, right? Not just the whole string itself, all the substrings. And how are we going to do that? Well, we're going to take advantage and use a prefix sum. So I'll show you how that works. Let's use this example. So A, C, A, D, A, C. Let's write all the prefixes. Also, rather than writing all 10 bits, I'm just going to write 4 bits because in this case, the most bit used thing is D, which is just the 4th bit. So let's just write out the bits for all the prefixes. So A would just be 0001, AC would be 0101, ACA. In this case, we're toggling the A again, so it's going back to 0. And then you have ACAD, which is 1100, then ACADA, which is 1101, and then lastly ACADAC, you're toggling the C, which means it's 1001. So out of these, you can clearly see like A is valid because there's only a single one. This is valid. Any of the other ones are not valid. So yeah, this makes sense right now. But now, how can we tell if any of the substrings are valid? Well, look here. How can we tell? This is not a prefix, right? It's a substring. How do we tell if this is valid or not? Well, it's actually quite simple. Any substring can be formulated by basically taking two prefixes and subtracting them. So this is one of the prefixes in this case, and this is the other prefix. So if we look at this, well, what is the red? What is the binary of the red, right? ACADA, it's 1101. Now, what about the blue one? Well, it's AC, right? AC is right here. It's just 0101, right? If we take the XOR operation, basically toggling it, we'll get 1000. What does this tell us? It tells us because in the D position, right, this represents the D, there's a 1 here, meaning that the occurrence of a D is odd, and everything else is even in the substring. And this is correct, right? In this green substring, only the D character appears an odd number of times. So yeah, when we look at this, we see, hey, there's only a single 1, which means, yes, this substring is valid. It's wonderful. So a key trick to this is you want to take advantage of the idea that there's only 10 bits, right? Because if you do an operation that loops through all 10 elements, well, this is basically a constant runtime operation, rather than if you were to generate every substring, which would actually be like somewhere around quadratic. So rather than basically checking this with every other substring and seeing whether it resembles some binary that has a single 1 or 0 ones, we're going to work backwards. So we're going to say, can we flip any of these bits here such that we can get another prefix that occurred previously, right? In this case, yes, if you flip this bit right here, then you'll get this prefix that occurred previously. And in this case, because you got that, that means you have a valid wonderful string. So basically, we're going to use a hash map for this to basically store all the previous prefixes that we've calculated. And that's basically the entire idea of this algorithm. We're just going to check, well, if I flip this bit, is there anything that matches in the hash map? If we flip this bit, we check all 10 bits individually, and that's how we can reduce the time complexity down to 10n. So yeah, I guess I'm just going to jump right into the code, and it should explain things a bit better. Okay, so let's get in the code. So we're going to first define a hash map. Let's suppose that the hash map initially has, if everything is a 0, then we'll just have occurrence of 1. This is just like a important initializer. Now we can define our mask and our res variable. And also what I like to do is, rather than looking at it as ABA, because we're going to do some bit operations, I want it to rather be like 0, 1, 0. So I'm basically just going to convert it to integers rather than letters, and you can do this in Python really easily by saying ord of letter minus ord of a for letter and word. So now comes the algorithm. So we want to loop through all of these, I guess, numbers now. So for num in list, we want the mask to be XORed with 1 left shifted num amount of times. So for example, initially the mask is like this. If we come across the character B, or I guess in this case, we're coming across A first. So we're going to basically left shift 1 0 times, which is just right here. So this is going to be toggled to 1 because we did an XOR. Then once we come across B, it'll XOR this one. And then when we come across the A again, it'll XOR this back to 0. So it's like a toggle, which is the XOR operation. And now that we've done that, we want to say if the mask is already in our frequency table, that means that there is some valid substring that is a wonderful string. So in this case, res is going to increment by frequency at mask. And it's important that we don't increment it just by 1, because what if this prefix occurred like multiple times? Then that means there's multiple wonderful strings. And now that we've seen it, we can increment this by 1. Otherwise, we'll just set its count to 1. Okay, so now comes the part where we're checking, like, if we flip all the 10 bits individually, like, is that in our hash map? So in this case, we can say if mask XORed with 1, rather we have to do a for loop for 10, for all 10 bits. So if mask XORed with 1 left shifted I times, so we're checking if we XOR at this bit for all 10 bits. If this is ever in our frequency, that means there is a wonderful string. So res plus equals frequency at whatever this guy was. And yeah, I think that really is the entire algorithm. So we can simply return res. We can try to submit it or run it first. Seems to be working. I think it's legit. And yeah, it seems to be passing. And yeah, in this case, the overall time complexity again is O of 10n, and the space complexity is O of n because we did use a hash map.